A few years ago, we had a whole event on bird song one spring down the road in another NYU building. And there, I was up there speaking about how the fact that, most birdsong scientists are interested in what birdsong is for. It's for attracting mates, it's for defending territories, it's useful, it's practical, end of story. What people weren't really studying is what's different about each song. Where's the aesthetics? What really separates a nightingale song from a sparrow song or a zebrafinch song? And in writing this book on birdsong, I came across many scientists who said what we're most interested in is what this song is for, what its function is for. But there I got to meet Ofer Tchernichovski, who's working at CUNY, and I said, why don't you look into the more complicated aesthetics of more complex, intricate bird songs, like mockingbirds or butcherbirds from Australia. How come people haven't studied those? And the standard answer is, it's hard enough to study the more simple bird songs, and so much is going on there. But he said, unlike many other scientists, that's a good idea. You should do it. So since then, we've been working on this. It's great to have people here who are really working on this lab on the aesthetics of bird song, right from the middle of cognitive bird song, neuroscience. And they're now moving, everyone's moved from City College to the Department of Psychology at Hunter College. So welcome Ofer Tchernichovski first, and then Tina Roeske.
So I don't know anything about evolution really, and so I'll try to talk very quickly about that. And, I got what I know something about is how to measure singing behavior, and we'll show you something that we learned about the evolution of culture in zebra finches, but then we'll fairly quickly move to more interesting birds, the nightingales, and Tina will take over and cover the musicality of nightingale songs, and then we'll take a question after we finish it together, okay? So yeah, I think that there's obviously beauty musicality in bird songs, and I don't like to argue about it, just listen and figure it out. But the point of the matter is that we heard a lot about the idea that we're talking about sexually selected trait as the engine behind the development of those forms. And nobody denies that. And but in general, when you think about the kind of, not really Darwinian, but what people call Darwinian sexual selection, is something that would mean that the structure of the song, whether it's aesthetics or whatever, should tell us something, should mirror some good qualities of the singer. But Prums said, and didn't actually mention it today, that one doesn't really have to assume that. You can, just the fact that there is some sexual selection happen can lead to very complex display patterns that are not adaptive at all. And David took it further, this kind of non-adaptive argument, by proposing that birds and whales, even though the singing behavior may be considered a sexual display, they may actually sing primarily to themselves, which is a very kind of interesting and crazy argument. So when I asked David, like, what do you mean by that? And he said, well, I mean that they sing because it's fun, because they can. And I was very stimulated by that, but I was also wondering, like, how can we make that interesting argument? Because I was always find it very funny that biologists that are too extreme, in the functional point of view, assuming that animals are not allowed to have fun, right? Because everything has to be functional. And I always find it a bit silly, because obviously animals like to have fun, like people do. And so how can we take David's ideas and turn them into something that we can actually measure dynamically in the laboratory? Because that's what I know how to do. So can we actually think about the evolution of something that we can call having fun by creating beauty? It is something that we can put biology in. So I will present some data about the evolution of song culture in zebra finches that can be actually seen a little bit in this slide, and I'll try to say why. And then Tina will tell us a little bit about what we are really trying to do, and not yet very successful, but trying to actually figure out musicality of birdsong in terms that people didn't do before. But I want to start with something bizarre, which again, I'm not an evolutionary biologist, I don't care using stupid terminologies, but I'll call it the evolution of self-stimulation. For a reason that you'll figure out in a second. And so self-stimulation, of course, gives those kind of two examples. But really, when we talk about behavior, many behaviors are self-stimulating, right? When a rooster crows, it's a very impressive call, right? I mean, the call is obviously not only communicative, but also very self-stimulating. And there are many other examples where we know for sure that the vocalization of the animal is self-stimulating, like in doves, female doves. But the point is that in all of those cases you heard before, we are talking about hardwired structure. So that the self-stimulation reinforces the behavior, but it doesn't create beauty. And what is interesting from that point of view, that songbirds were a point in evolutionary history where probably the first time in evolutionary history, the beauty can actually be formed by the self-stimulation. How can that happen? Well, usually we think about singing behavior as a learned behavior and as sexually selected traits. Of course, the young animals are learning their songs from their fathers, the females are listening, admiring, and responding. And a lot of the attention, almost all the attention, was placed into the issue of song learning, how the bird is capable of imitating the song of adult birds. Very, very interesting question. But the more primary question is what the bird is doing to himself. Because what really happened to a young bird that sings these very unstructured sounds, what we call subsong. It's very unstructured kind of sounds. Those sounds are very sensitive to feedback of the bird's own sound. So if this bird cannot hear himself, he cannot develop a song. If he hears himself, he can develop a very interesting song, which is not yet a normal song, but very interesting song. You will not see that in a rooster. Rooster does not need to hear himself to create completely normal crow. But what is that kind of process, this very kind of fast kind of evolutionary process within the same bird from moment to moment, where this auditory feedback shapes the structure of vocal sound? We really don't understand much of that. But we can assume for a moment that the bird is starting by machinery in his mind, in his brain, to produce a repertoire of variable sounds that are unstructured and doesn't sound very good, most of them. But he's using his auditory feedback and some kind of a reinforcement learning without any kind of other birds around even, to practically evolve some structure. And if you think about it this way, then we could just say, that if something that you do sounds pleasing, then you can shape those sounds in that direction. And that's actually what they do. They do it from moment to moment. But then, what is it that can make a vocal sound pleasing? From an evolutionary point of view, I don't know what the answer is, but as Richard Prum noted when we chatted about it, it's not a coincidence that flowers attract both pollinating insects and humans, right? There is something in brains that is responding to beauty in a level that is maybe very, very kind of primitive. But what we mean by that, I'm not quite sure, but you can think about like some kind of a backdoor access to pleasure area. Whatever evolutionary history designed your brain, stimulations are almost never neutral. Everything drives you to feel a little bit better or a little bit worse. So even if it has no adaptive things whatsoever, just the fact that you are making those sounds that are making the brain process in all kinds of ways, it's somehow activating those areas, generating this kind of self-feedback very, very quickly. So of course, some of those may be very universal, like maybe between insects and humans, but some of those could be actually very species-specific or very human-specific, right? Or animal-specific. So without even putting too much attention to those details, let me just claim a little bit how this may apply to birdsong. So generally, if you take a songbird and raise him in a complete isolation, social, auditory, anything, the bird will still develop a song that has an interesting structure. And this structure requires auditory feedback. Auditory feedback is essential. So you need to hear himself to create that. But we don't know how. But if you look at the song, the abnormal song of isolate songs, it might by itself mirror some kind of self-reinforcing patterns. And the question is, can we actually measure those patterns? And maybe those kind of self-reinforcing patterns are the aesthetics that maybe can be more universal in one case or more species-specific in another case. So I'm going to show you some study that we did finished a couple of years ago about the first phase of evolution of song culture that can be interpreted in this light. And I never actually thought about it this way carefully until 2 days ago when I was starting to work more seriously on this lecture, and I figured out that I didn't understand what I was doing. So the development of song culture in zebra finches, this was done in my lab, also by some collaborator. Partha Mitra Okemati is the original idea of doing the first experiment that I'll show you. Olga Feher, who did her PhD on that, and Haibin Wang, who did much of the analysis with us. And the question that you start with is the isolate song, a song that the bird developed all alone, when it has nothing to imitate. Isolate songs sounds bizarre compared to other zebrafinch songs, but they are still quite structured. So I'll just let you hear two examples. Here's one. Here's another one. And anyone that knows zebrafinch song, it doesn't sound right. That's how normal zebrafinch song sounds like. Like here's one example. Here's another one. So if you look at them, even those kind of sonographic image, and you just look at the colors below, you can see that there are a lot of differences between them. And the question that we ask ourselves is, first of all, how this original structure comes about, and how it develops into the wild-type song, which is an outcome of a lot of imitations. So that every time that you take a zebrafinch and listen to that bird is singing a song it imitated from other birds, who imitated from other birds, who were selected by female, and all those kind of things are happening. So there's always a lot of history there. Whereas in the isolate song, there is no history. This is just what the bird is doing by its own. But what is really required to go from here to there? And here you can have immediately a few ideas about how it can happen. One way it can happen by sexual selection. It can be that you start by an isolate bird that sings a song that is not very nice, so the female won't like him. Another one sings an isolate song that is maybe a little bit nicer, the female likes him more, so that's just regular sexual selection. Another idea is that maybe you don't even need the female for that particular development of structure, maybe just enough that the males who share the same genes with the females also have the same preferences when they imitate. So they imitate some syllables and will not imitate other syllables. But there's also a third idea of what we call biased imitation. This will be a non-Darwinian process, which is still an evolutionary process, where the bird is imitating things, but changing them as he's imitating them because of some internal tendency to do it differently. So the kind of experiment that Olga did was really very simple. You take a bird, raise it in isolation, and then you have an isolate bird with an isolate bizarre song. You now take this bird, put it in a soundproof chamber together with a young bird. Let the young bird learn the song from this bird, and then use this young bird as a tutor in another box. So you always do it one-to-one, and you do it recursively, right? So what you're really doing, you're amplifying those kind of changes, right? Because every time, and you do it without any females, so there are no females here at all, and there is no audience except for the tutor people, right? And you just want to see what happens when you do this kind of recursion of imitation of the isolate song. And to our astonishment, 3 or 4 recursions like this are sufficient to generate a completely normal wild-type zebrafinch song. That's all you need. So that's all already encoded in the bird, right? You only need to do this kind of recursion. So what's going on there? I'll just show you some example. Here is a song of an isolated zebrafinch. And listen to the imitation of the pupils. They imitate, but it's sort of different. And look what happened in a later generation, just 3 generations down the road. So you can hear that it's changing. So when you look at the evolution of particular imitation recursions, you can see what's going on. You can see here, for example, that the imitation is biased the syllable structure from one generation to the next in a particular direction. And we can do it in different ways, and we usually get the same kind of trajectories. Here's an example of another tutor. Very bizarre isolated song. Here is the imitation. So again, they go for it, but not all the way. and the question is what's happening. Here is another example, for example, of imitation of isolated song, and you can see that many syllables are imitated accurately, but the one that is long, like goes like this, is imitating in some kind of a compressed version. So when you look at those kind of biases, and I won't sort of like bore you with the quantification of those are very systematic biases. Another example, the higher level bias, is an isolated song that sings a song that actually sounds more like another species, a little bit more like a canary song. So you can see that he repeats the same syllable again and again. It's completely forbidden in a zebrafinch colony. They always do like A, B, C, D. They never do B, 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 B like that. You can see that the imitation is already solving the problem. It is avoiding those kind of sequences. So overall, we can see this kind of de novo emergence of the wild type structure very, very quickly, just by the recursive imitation. It's definitely not sexual selection. There are no females there, and there is no selection. It's not a Darwinian process because they're not selecting subsets of the syllables, they're just morphing them. And this is definitely some kind of a biases. Without getting too much into the nature of those biases, those were already published, I'll just tell you very quickly that the biases are towards shifting features to have durations that are between a range of 30 to 230 milliseconds, which is exactly the wild type range. The imitation is biased toward creating linear sequences and avoiding repeats. And it's biases toward maybe certain rhythms and certain syntax. And maybe all of those are sort of like self-stimulating for the animals. That's the kind of thing thought that we have to have. Maybe some symmetries are more pleasing. But the question that is really leading us to think about is that if it's all encoded in the bird's perception, those are all kind of preference biases in the imitation, are those things really can be studied more carefully by looking at musical structure. Keep going? Okay. So I'll show you a little bit of data with thrush nightingale song structure, and then Tina will continue with the European nightingale. Those thrush nightingale data is something that David gave me early on in our collaboration. And those songs are fairly complex, but not as complex as the European nightingale in some respects. And here I'm just showing you like different parts of the song. Here is like the first part, what you see highlighted here. You can see a blow up of it below. So you can see it's pretty complex spectral structure. Let's listen to it. And then it goes here. And here are those kind of click. Look at those are actually going in duos. You heard in the end? It goes louder and louder. Right? Here are like three trios. And look, there is a little click right here. Try to listen to the rhythm here and notice where the arrow goes. You heard it? Some click that goes there. So it seems to be very rhythmic and very nicely structured. And here are 30 songs of the same, 30 seconds of singing in that same bird. And you can see that it's very complex to try to figure out what's going on. And we want to look at the entire performance of the bird. So what I did here is try to quantify the entire singing behavior, 1 hour of complex singing, try to put it together in a way that we can understand what's going on. So to simplify the song, we can just look at simple features like the pitch contour of the sound. We can segment it to different syllables, measure the pitch, and measure other feature like the width of the power spectrum. For example, you can see that the sounds towards the end are broadband sounds, with like fricative kind of sounds. The sounds in the beginning are more like whistle, like high tone sounds. We can look at the entropy of the spectrum to actually quantify that, which is the winner entropy right here. But just go very quickly through that. We have now only two features to describe each sound: the pitch of the sound and how tonal it is. Those are the kind of two features. So now we practically take those syllables and we look at their features, and we can just plot them. Where on the x-axis I'm showing you the tonality, and on the y-axis I'm showing you the pitch. So sound that has a very kind of a fricative nature will be here. Sounds of low pitch that are tonal will be here, and high pitch will be there. So if you look at the entire performance of a bird, it may look like that. So now you can see that this bird is doing very fricative sounds here. He's doing low pitch tones here, and high pitch tones here. So this may sound like this, those sounds. Those will be the low. Those will be the high. But now compare this bird to this other bird. You see that there's a difference between the performances here. And look at this bird, for example. So different birds have different contrasts between those. They all seem to have those kind of fricatives versus low pitch versus high pitch, but with different contrast and with different emphasis. So what would be interesting to see, if those really mirror something in terms of the aesthetics of the song that is important for the bird or for the listeners or both. In terms of time structure, you can try to think about how quickly can you move from one type of sound to the other by just looking at the onset interval. So how fast can you see? Well, you can measure that by just looking at the onset interval, but you can think very fast if you don't try to put structure. If you try to put structure, then we go for the second variable, which is the tonality. So what will be hard? What will be hard is singing fast, very, very, very structured tones. So practically speaking, if you're looking here at the bottom, at the origin of the axis, this will be fast with good pitch. Then you can do fast fricatives. Then you can do slow down with good pitch, and probably the worst will be slow fricative. Something like that. So how do they really sing? Well, when you look across all the birds, you can see immediately that fricatives tend to be much faster than the tonal one, so that they're trying to avoid those kind of sounds. But if you look at individual birds, you see different performances. For example, this bird here that you see in the red, it's quite easy to see that there is some kind of a compromise that the bird is making. So that when he's close to the origin of the axis here, so that he's doing sounds that are very tonal and very fast, he actually cannot go as fast as he can go here, right? So there's a compromise. Either you do it very tonal, very good, or you do it very fast, right? You have to decide where you go. But this compromise is only for this bird. This bird doesn't seem to make any compromise, right? He's capable of doing it this way. Again, is he giving up on something else? Those kind of performance parameters, I think, are going to be interesting to try to figure out. So again, in terms of song performance, we talk about the transition speed, the repeats and the symmetry, about the contrast between the fricatives and the tonal sounds, and some compromises between the acoustic purity and the speed of transitions. So now Tina will present what we are trying to do more seriously in terms of the musicality.
Part 2. He dared to be bewitched by the beauty of the nightingale song. And here's what came out.
I hope all the audio will work now that I transferred the talk to a different computer. So the nightingale in this picture is probably producing a wonderful and complicated sound here. And other nightingales listening to him might think he's a musical superstar. But actually about this individual we don't know, so just as well he could be an amateur or even a really bad bungler. Traditionally biologists have emphasized that this will have an effect on his life. So it will probably affect what kind of mate he will get. And and maybe what kind of territory he will be able to defend. But in the next 15 minutes, I'm going to present you now how we are approaching performance differences in Nightingale's song in a more musicologist way. Music elicits emotions and changes behavioral states, which is really nicely illustrated in this kitchen picture here. And I think we all know about it from our own listening experiences. Music is able to do so because our brains are designed to attribute emotions to perceived scenes. So what music does is actually create an auditory scene that is designed to elicit certain emotions. We are wondering now whether this is true for birdsong too. So in other words, are birds thrilled when they sing or hear a particularly beautiful song? And is there something, as can be said for humans, like an aesthetics of birdsong that we can scientifically investigate? So far, as you heard before, researchers mostly try to avoid such questions because they seem too fuzzy and not scientific enough. But of course, there have been exceptions like David. And so among other books, in this new book, he's trying to promote the idea that aesthetics in animals can be studied scientifically. And regarding to birdsong, it is striking how beautiful birdsong is, even across species boundaries, even to us. That birds put so much effort in producing these complex sounds. So obviously they're not trying to produce just the longest shrieks or the loudest shrieks. They're really producing a complex sound, and in the same way as human music can be studied scientifically, we would like to try now to investigate birdsong in such a way. Of course, this would require a completely different terminology to what has been used so far by biologists. It would be closer to the terminology of musicologists investigating something like themes, variations, rhymes, stuff like that. Now, how can we start if we want to investigate birdsong in such terms? We got a lot of inspiration from this book by David Jaron, a musicologist from Ohio State University, that's called Sweet Anticipation. His approach to music is a psychological one. His idea is that statistical properties of music make us form musical expectations just in the same way as we form expectations about other aspects of the world, just by statistical learning about things we encounter. And David Jaron's hypothesis is that music elicits emotions by either confirming or violating these musical expectations. Now what we try to do is to measure statistical properties of nightingale song that might be able to elicit such musical expectations and perhaps emotions in the birds. So we try to find sort of deep structures in the nightingale song, statistical structures that are shared by groups of songs. Then we can ask whether nightingales play, like musicians, with the musical expectations of their listeners. And we're trying to do so by identifying performance differences between individuals. These two guys are Mark Nagib and Philip Sprau, and they are the ones who did the recording. So they did the dirty field work and robbed around in parks during the night because nightingales sing mostly at night. And they gave us their data. This is a male nightingale.
Could you speak into the microphone?
Sorry. A European nightingale. And they're really amazing singers. They have more than 200 song types. These song types in one performance, they're between 2 and 10 seconds long and are separated by little pauses. And they can sing over hours during the night in breeding season. These nightingales, our recordings are from northern France, and the birds are migrating. They're territorial birds. They're migrating during winter to Africa, and they come back in spring to breed in France and the rest of Europe. You're going to hear now nightingale songs, and here they're represented in two different ways. On the upper panel you see oscillograms, which is amplitude over time, and in the lower panels you see sonograms of the same 6 songs, which is basically frequency over time. So there are 6 songs shown, and I'll play the first 3 of them now in normal speed as they are in nature, and then you'll hear all 6 of them slowed down, because slowed down it's much easier for human ears to assess the structure in tune. now. You'll hear this, all 6 of them slowed down. Project as a sort of fishing expedition because, of course, we don't know which properties or parameters of the song are really relevant and meaningful in terms of musical expectation forming and individual differences. I'm going to present my results in two parts. First, I'm talking about the quantification of some melodic properties of pitch in comparison with human music. And then I'll talk about performance differences between individuals. So, to analyze melodic properties of Nightingale song, as Ofer already presented, we first did a syllable analysis where we cut up the song into syllables, calculated features like amplitude, pitch, and so on. And those features I'll show you in the following. In human music, we find a phenomenon that's called step inertia. It means that small intervals that are called steps are inert with respect to their direction. So melodies that are going up, like da-da-da, are more frequent in human music than melodies that have a directional switch, like da-da-da, up-down. And melodies that go down-down, da-da-da, likewise are more frequent than down-up, da-da-da. And a nice example is the song Row Your Boat, and I'll show you an animation in the next slide. But of course, we are wondering whether this is true for Nightingale song too. This is the kind of plot you'll see then for the Nightingales, but I'll illustrate now the song Row Your Boat so you understand where you can see step inertia. In these graphs, we plot pitch intervals within a melody against the following pitch interval. It means that a melody that is going up will be in the upper right quadrant here, because the first interval is going up, so it's going to be on the right side. The second interval is going up too, so it's going to be here. So the quadrant shaded in blue will represent step inertia. Step inertia, while the other ones represent the opposite. And as the song Row Your Boat now progresses, you can see the dots coming up in this plot. So clearly there are more blue dots in the step inertia representing quadrants here. But if we did the same thing now, the same kind of analysis for Nightingale songs, we see quite the opposite. Here, most of the dots are clearly in those other quadrants. So the Nightingale melodies show something that we can call step reversal rather than step inertia. It's quite the opposite of what we find in human music here. So consecutive pitch intervals tend to rather differ in direction. What might be caused by those trills that Nightingales often make at the end of their song, with two kinds of notes that are like da-di-da-di-da-di-da-di-da very, very quickly. And humans make that much less in their melodies, which are more, they have more melodic lines like da-da-da-da-da-da-da-da, something like that. So in Nightingales, the same is true not only for large intervals, but also for small intervals. So unlike human music, Nightingale songs show something like step reversal rather than inertia. And we're of course wondering why human music and Nightingale song could have such different melodic structure. So one possible explanation is that they really have different aesthetics or different taste. And to check for those, we could run preference tests with nightingales, where we manipulate the song they're listening to into something that sounds more human-like, with long melodic lines, as opposed to what they normally do in those trills. This hasn't been done yet, but it would be an interesting thing to analyze. But of course, we also have to consider other explanations. There might be just constraints on sound production in the male nightingales. For instance, a tendency to rather generate really high and really low pitch that would automatically lead to more switches in pitch within a melody then. Do I have still time to?
Yeah, like 7-8 minutes. Yeah.
Okay, I'll try to be quick. So the second part of my talk is performance differences between individuals. So if nightingales, like musicians, play around with musical expectations of their listeners, we should assume that they are better and less good performers. So some are probably better able to introduce variations in more interesting ways and or to balance stereotypy and variability smarter than others. So the most obvious individual differences have been described in detail already. They're repertoire differences. So males of the same population, they share many of their song types, but also they have some types that's just a small, that might be very individual, that only one individual is singing. And we are now wondering whether these differences are meaningful with respect to aesthetics. So in other words, there might be better and less good sounds in a nightingale repertoire, or nicer ways to combine certain sounds. To find out about this, we have to characterize the song space first of a population, but also of an individual, and that means classifying songs. And of course, there are definitely many ways of classifying songs. So the one I'm going to present here is a very, very simple one with which we just started. It's a classification according to rhythm, and it's still very rough. So what we do is we sample amplitude continuously for each song in a whole performance. So each song gets an amplitude time series. The amplitude you can see here is the yellow graph. And then we convert this to color code, where high amplitude is represented in warm colors like red and yellow, and low amplitude where there's no sound is blue or green, and thereby we can somehow capture the rhythm of the sound. What we do then is to align all songs of an individual to the first introductory note. Then we plot the songs in color code, the amplitude time series, and then we plot these amplitude time series of one individual altogether. So here you see all 500 something songs of one bird that he sang in one performance. Each of these tiny lines is one song. It's the amplitude time series of one song. And this is a very nice way of looking at an entire performance of a bird. And while in the beginning you can see some rhythmic structure, so you see these vertical lines that correspond to notes and pauses, it's still a very messy picture. And what we did to classify these songs, to group them somehow, was clustering them just according to similarity of the amplitude time courses. This is the result of such clustering. You see the cluster now. We just told the algorithm to generate 10 clusters, so that's kind of random. But already with this coarse method, we see much more structure here. We can see those vertical lines representing a rhythm until much farther in the songs, and also they are sorted according to song length. And if we go now into the clusters and have a look whether they are meaningful, we can see that in the upper panel there you see 2 songs from cluster 6, and beneath the color-coded amplitude time series you see the sonograms, and you see there that although the notes are very, very different between these songs, they really do have a common rhythmic theme somehow. And the same is true for the 2 songs from cluster 8, which are very different from those in cluster 6. On the left here you can see now more than 6,000 songs produced from our entire bird population, from 14 birds altogether. And on the right side, you see all these songs of the population clustered by similarity. So in each cluster, in this case, we have now songs from different birds, from 14 different birds. And to see now whether individual birds make individual use of these song classes, we did the following kind of plot. The song clusters were plotted as circles here. And the song order, as being sung by an individual, is represented by blue lines between those dots, between those circles. So what we see in this kind of plot are two things. First, we can see which clusters are produced adjacent to each other. So songs from which cluster are produced adjacent to each other. And also we see which clusters are being most used by an individual, because those will receive the most lines. So here you see 6 birds' usage of these song clusters. And as it's easy to see in the very different patterns, they use different clusters in their performance. Bird 1 used a lot of this cluster, bird 3 a lot of this cluster, and so on and so on. So these patterns look very different between individuals, which means they just use very different subsets of songs in the population, although they do share a lot of these songs. Now, we're not there yet, but of course we're interested in finding out what's the significance of the variability in repertoire usage across the birds. So what we want to find out next is whether there are combinations of song types that go together better and are more appealing to first the females, but also the singer himself. And so this was just what I presented here was a first attempt to do a more musicological analysis of birdsong. But of course there are many open questions, and we have to think about in which directions to go. So when we compared here melodic properties between nightingale song and human music, and found that they were different, we are now wondering whether music theory might help us understand how birdsong may affect behavioral state in other birds and perhaps emotions. And also a second question we are really interested in is to what extent song structure is determined by what singers like and what the audience likes, what females might like. So we will need to develop methods to assess how song evokes pleasure and emotions in the singer himself versus in the audience.
Thanks so much, Tina. You can see how hard it is to get inside the aesthetic of an alien species, even one making such beautiful songs that humans like so much. Okay, we can take a few questions while Anna is setting up. So it'll be a little bit messy as the next presentation has a few items need to come onto stage, so go ahead.
Hi, I enjoyed that very much. Do you have an initial idea as to how to measure if a bird pleases himself with his own song?
Oh, wait, would you like to answer the question? So you might check for dopamine levels in the brain or other physiological measures, or maybe here.
Yeah, we are now succeeding to use a PET scan to non-invasively measure dopamine response to songs. So we can, just about 2 weeks ago, figured out that we can do it.
I'm curious if you have measured the same bird and his song over repeat performances, and if he repeats the same order again and again, or if he also has variation within his own singing.
I haven't done it, but people did that before, and also we have data from several years, so we could even compare between sequential years. And it seems there are big individual differences, and some of the birds seem to prefer certain orders of individual song types, and others seem to be pretty random. And it would be nice to know then about mating success, for instance. But I'm not sure we have the data yet, but in principle, of course, we can investigate it.
I find that your visuals, your graphics there are actually very beautiful, very aesthetic things. I'm curious whether if you get data from the dopamine, is that data likely to be mapped into the similar graphics, or are we going to see some completely different type of mapping? Do you have any anticipation of how you will record that data?
Well, recording, but more about how to present it then.
Yeah.
But I'm sure you could find really nice ways of intertwining the auditory data that's recorded then together with the dopamine data, and maybe there are particularly beautiful ways in representing them. I don't know yet. Maybe we should find some artists to help us with that.
Okay, one more question from over here. Someone has a mic.
Hi, thank you so much for your presentation. I was curious if your studies study the birds in their natural habitat, where weather patterns and the sounds of other animals, the sounds of other birds, the sounds of the environment within the bird naturally is, would perhaps be reflected in the bird's song, or are these birds being studied in the laboratory?
These songs are all from the wild, and the good thing about nightingales is that they do sing at night, where there's very little interference from other animals. But sometimes they engage in counter singing, so they sing together, and that does affect, for instance, the pause length between the songs, and also it might affect which songs are being sung in which order, because they might respond to another bird singing. But these recordings have been, well, at least as good as we could, controlled for counter singing and for such effects. So there shouldn't be too much of that. But this is another interesting thing. I mean, you could definitely sample data when they sing during the day and see how different it is for nightingales.
Thanks.
Thanks so much, Tina. A few years ago, we had a whole event on bird song one spring down the road in another NYU building. And there, I was up there speaking about how the fact that, most birdsong scientists are interested in what birdsong is for. It's for attracting mates, it's for defending territories, it's useful, it's practical, end of story. What people weren't really studying is what's different about each song. Where's the aesthetics? What really separates a nightingale song from a sparrow song or a zebrafinch song? And in writing, in writing this book on birdsong, I came across many scientists who said what we're most interested in is what this song is for, what its function is for. But there I got to meet Ofer Tchernichovski, who's working at CUNY, and I said, why don't you look into the more complicated aesthetics of more complex, intricate bird songs, like mockingbirds or butcherbirds from Australia? How come people haven't studied?
Something should mirror some good qualities of the singer. But Rick Prums said, and didn't actually mention it today, that one doesn't really have to assume that. You can, just the fact that there is some sexual selection happen can lead to very complex display patterns that are not adaptive at all. And David took it further, this kind of non-adaptive argument, by proposing that birds and whales, even though the singing behavior may be considered a sexual display, they may actually sing primarily to themselves. Which is a very kind of interesting and crazy argument. So when I asked David, what do you mean by that? And he said, well, I mean that they sing because it's fun. Because they can. And I was very stimulated by that, but I was also wondering, how can we make that interesting argument? Because I was always find it very funny that biologists that are too extreme, in the functional point of view, assuming that animals are not allowed to have fun, right? Because everything has to be functional. And I always find it a bit silly, because obviously animals like to have fun, like people do. And so how can we take David's ideas and turn them into something that we can actually measure dynamically in the laboratory? Because that's what I know how to do. So can we actually think about the evolution of something that we can call having fun by creating beauty? It is something that we can put biology in. So I will present some data about the evolution of song culture in zebra finches that can be zebra finches, but then we'll fairly quickly move to more interesting birds, nightingales, and Tina will take over and cover the musicality of nightingale songs, and then we'll take a question after we finish it together, okay? So yeah, I think that there's obviously beauty musicality in bird songs, and I don't like to argue about it, just listen and figure it out. But the point of the matter is that we heard a lot about the idea that we're talking about sexually selected trait as the engine behind the development of those forms. And nobody denies that. And, but in general, when you think about the kind of, not really Darwinian, but what we could call Darwinian sexual selection, is something that would mean that the structure of the song, whether it's aesthetics or whatever, should tell us.
Study those, and the standard answer is it's hard enough to study the more simple bird songs, and so much is going on there. But he said, unlike many other scientists, that's a good idea. You should do it. So since then, we've been working on this. It's great to have people here who are really working on this lab on the aesthetics of bird song, right from the middle of cognitive bird song, neuroscience, and they're now moving. Everyone's moved from City College to the Department of Psychology at Hunter College. So welcome Ofer Tchernichovski first, and then Tina Roeske.
Okay. So I don't know anything about evolution really, and so I'll try to talk very quickly about that. And what I know something about is how to measure singing behavior, and we'll show something that we learned about the evolution of culture in